Up. And there's a charged particle. Let's say a proton. And goes this way, comes in horizontally, traveling that way. So when the proton is here, moving this way, what will be the direction of the magnetic force on it? Maybe let me get out of the, so you can see the board and see the expression. Which way will be the force on this proton? It's a proton, so it's positively charged, right? So the direction of the magnetic force will be in the same direction as the cross product. The velocity is to the right, to your right. The magnetic field is up. Which way?
So it's going to come towards us?
Towards you. And by the way, this is the velocity of it, and this will be the force on it, right? Can you see that the force is perpendicular to the velocity vector? I mean, I don't have to do this. You can see it right here, right? This magnetic field is in the same or in the opposite direction as this cross product. And remember that the result of a cross product is perpendicular to the two vectors that you multiply. So the force has to be perpendicular to the magnetic field, and it has to be perpendicular to the velocity. What do you remember from Physics 185? If the force acting on a particle that's moving is perpendicular to the velocity. Think of F equals ma. If the force is this way, it will give the object an acceleration that way, because the mass is positive. So what happens when the velocity is in some direction and the acceleration vector is perpendicular to it?
Curves.
Does it speed up? Does it slow down? Right? If the acceleration vector is in the same direction as the velocity vector, the particle is going to speed up. If the velocity vector is opposite to the acceleration vector, the particle is going to slow down. But if it's perpendicular, well, this acceleration vector doesn't have a component in the same direction to make it speed up, and it doesn't have a component in the opposite direction to the velocity vector to make it slow down. But there's a force in there. So it'll make it, this acceleration will make the velocity vector change by causing the velocity to change in direction without speeding up or slowing down. So what will happen is that if the proton travels this way, a positively charged particle, I made it a proton, right? That the force is going to be this way. This force will not speed up the proton, it will not slow it down. It's going to make it turn. Well, imagine it goes this way and it's getting pulled that way, the proton is going to go here. Now, what happens when the proton gets here? The magnetic field is still up, I said everywhere in the room. So if the velocity is this way, and the magnetic field is up, what is the direction of the force on the proton? That's now moving this way because it turned, because magnetic field exerts a force that way. To the right. And again, it's perpendicular to the velocity vector, so it's not going to make it speed up or slow down, so it's going to make it turn this way, so it's going to make it go this way. And what happens when the particle now is here, when the proton is now here? The force is going to be which way? Towards the front. So it's going to turn this way. And when it is over here, what will be the direction of the force on it? To the right. So what will happen is that, it'd be nice to see this, right? I throw the keys and the keys go zzz in a circular path. Uniform circular motion. And the magnetic force it's a force towards the center, it becomes a centripetal force, which gives the proton a centripetal acceleration. And we can figure out the radius of the orbit if we know the speed and the strength of the magnetic field and so on. So, if there is a magnetic field over some region of space, and there's a charged particle moving perpendicularly, like I did, right? I deliberately threw it perpendicularly to the magnetic field, then the magnetic field will move in a circular path around the magnetic field. In a circular path on a plane that's perpendicular to the magnetic field. Yes? And we can calculate the radius of the orbit and so on. What happens if instead the proton, instead of coming into this room, traveling horizontally, suppose the proton goes into this room traveling at an angle, like this. So the velocity of the proton is this way, the magnetic force is like that, right? Up. Well, this velocity vector, let me use this one instead, or this one. This velocity vector, any vector can be replaced by its components, right? So I can replace this velocity vector by a component that's vertical and the other component horizontal, right? So this velocity vector can be replaced by two components like this, right? A vector like that, vertical component, a horizontal component. We know what this velocity is going to end up doing, right? It's going to make it go around. But what about this velocity vector?
It's gonna make it go up and then back down.
What did we say? If the particle has a velocity in the same direction? So this velocity component is in the same direction as the magnetic field. Magnetic field is not going to change this at all. This one is going to change in direction, not in magnitude. So what will happen is that this velocity component is not going to change. It'll just go up, 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 but at the same time, it has to go around. Because this other velocity component is responsible for it making it go around. So what will happen is that the proton were coming in at an angle, the proton would come in, and then it would go around the magnetic field line in a spiral.
How can it still going up if there is no force? Or
The force is created by the magnetic field. See, it's not so. Okay, let me rephrase the question. Not my answer. The particle comes in at a velocity like this, right? So this component of the velocity vector, which is perpendicular to the magnetic field, is going to result in a force like that will make it turn, right? But the particle comes in with this velocity vector component as well, and the magnetic field is not going to exert a force on the particle, as a result of this velocity. So if that force is zero, then this velocity will stay constant. F equals ma. If the force is zero, the acceleration is zero for this velocity component, so the velocity will stay the same. This component. The other one is going to change in direction. This other one is unchanged because there is no force attributed to this component of velocity. So, right?
Yeah.
So zero force doesn't necessarily mean that it's going to be at rest. Zero force means that the velocity is not going to change, but it came in with that velocity, so it'll just keep that velocity. So it'll go up and spiral around. Yes. And the sun likes to spit. Oops. It may be angry. Oh, people are having too many wars on Earth. And sometimes it spits in our direction. And what happens when the sun spits in our direction towards the Earth? Well, technically, the sun ejects a mass, coronal mass ejection. There are names given. I like to think of the sun as spitting. So this is the sun, shines light, but sometimes it spits this way, and that's matter that's just coming this way. And most of this, the sun is mostly hydrogen. It's got helium, like roughly 75% hydrogen, 25% helium, and traces of other heavy elements. So this is, let's say, like protons, electrons, like charged particles, right? Plus, minus, and they're coming this way at very high speed. And here's the Earth. So this is Earth. And this is where Santa lives, in the North Pole. Right? South Pole, equator, and the Earth generates a magnetic field. And the Earth magnetic field is roughly like this. actually it comes out here, it goes up, back into the earth. And remember that I said that, you have these closed loops? So, actually what happens is that the magnetic field of the earth goes in and then it comes out over here, right? It goes in, comes out over there. So this is the earth magnetic field. Which is actually a good thing. Because a lot of this high speed, high energy charged particles ejected from the sun, sometimes towards the earth. What happens? The charged particle comes in. What are the chances that it comes in at exactly 90.000000000000000 degrees to the magnetic field? Because if it did, it would just go like. But chances are that it's going to be a little off, or a lot off, and the charged particle is going to end up spiraling around the magnetic field line. Or, depending on how they're coming in, they might spiral along the magnetic field lines of the Earth. And the Earth isn't. The Earth also has what? An atmosphere, right? Not to scale over here. So this is the Earth atmosphere. And what? You have like 78% nitrogen molecules, 18 or so percent oxygen molecules, carbon monoxide, carbon dioxide, other crap, blah, blah, blah. The atmosphere is made up of molecules, atoms, and so on. And what happens when these charged particles coming in from the sun, right, are then, deflected by the Earth magnetic field and sent to the north or the south poles? What happens when these charged particles then enter the Earth atmosphere? Then, boom, boom, boom. They collide with the molecules, atoms that make up the Earth atmosphere, exciting those molecules to higher energy levels. And if those molecules don't get hit soon afterwards, they relax back to their lower energy states. And the energy that they received in the collision now gets emitted as
Thermal energy?
light. And so there's a light display here and here. And people call these the northern lights. Like in the Polar Express movie, right? What are they called? The Aurora Borealis?
Yeah.
If it happens in the North Pole, and if it happens in the South Pole, the Southern Lights or Aurora Australis, like Australia. So every time there's a light show in the Northern and North Pole and the South Pole, the sun was spinning towards the Earth. And it's actually a good thing that we have this magnetic field because, most people live in these regions of the Earth, right? Because it's, how many people live, over there, and how many people live over there? So most of the, population is in these regions, right? And people like me, without protection up here, if the Earth didn't have a magnetic field, right, those high energy charged particles will come in and just boom, 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 and cause mutations in cells, which could turn into cancerous cells, skin cancer, or who knows, maybe I'll grow hair again, right? But it's a good thing that the Earth is shielded by this magnetic field because it serves to protect us from incoming cosmic rays of high energy, right, that could otherwise cause some damage. And so, this is something that can be understood in terms of this expression. Right? So you start analyzing that expression. This is a cross product, right, which has to be, it's going to be some vector that's perpendicular to both of these, right? So if the charged particle is positive, like it could be, there are positively electrical charged particles and there are negatively charged particles. If the charged particle is positive, then the force acting on the charged particle will be in the direction of this cross product. But if the charged particle is negative, like electrons, they're negatively charged particles, muons, then the force acting on those particles, right, exerted by the magnetic field, will be in the opposite direction to this cross product. Either way, the force has to be perpendicular to the velocity of the particles, which means that magnetic fields can deflect charged particles, can change the direction of travel of a charged particle, but it is not going to speed it up or slow it down, right? So if an object has a velocity this way and the acceleration is that way, first of all, if it has an acceleration that way, it has to have a net force that way, right? Because the relationship between this vector and this vector is that the net force is ma. And the mass of any particle, I don't care if it's an electron or proton or whatever, is positive. Unless it's a photon, which doesn't have any mass. But if a particle has mass, it could be ridiculously small, but it's going to be positive, as far as we know. So therefore, this vector, the net force, has to be in the direction of the acceleration vector. So if the acceleration is to the right, there has to be a net force to the right, right? And if this is the case, the particle speeds up. But if the particle of mass m is going this way and the net force is this way, that's because the acceleration has to be that way, and in this case the particle slows down. Right? So if the acceleration vector of the particle is in the same direction or opposite direction to the velocity vector, it'll speed up or slow down. Well, if the acceleration vector is perpendicular to the velocity vector, then the component of this acceleration vector this way in the direction of the velocity is 0, so the particle doesn't speed up. And the component of that acceleration vector this way in the opposite direction to the velocity vector is also 0, so it doesn't slow down. So if there is an acceleration this way, there has to be a force that way that's going to make the particle change direction of travel without speeding up and without slowing down. So magnetic fields are used to deflect, to make charged particles turn without speeding them up and without slowing down. You want to speed up a charged particle, you use an electric field. Right? If the charged particle is moving that way, let's say it's plus, right? Then put an electric field this way, maybe plus, 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 and minus, 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 minus. This electric field, right, will result in this force of the charged particle. And if this is plus, then this force will be in the same direction as the electric field. So the force is going to be this way, giving it an acceleration in that direction. And then it can speed up. Right? So electric fields are used to, speed up, slow down charged particles. Magnetic fields are not used to speed them up or slow them down. Magnetic fields are used to steer them, to make them go this way, that way.
Professor, I'm just a little bit confused with that illustration there on the right. You said that if that charged particle came in at exactly 90 degrees,
then it would go around the magnetic field in a circle, like I discussed when we had it like this.
Yeah.
So it wouldn't go up and it wouldn't go down. It would just go around the magnetic field and it would stay trapped.
Okay,
But if it's coming in as an angle, then as small as that angle may be, it's going to have a velocity component in the same direction as the magnetic field.
It's going to be slightly deflected.
So what?
It'll be slightly deflected, not.
So no, so the charged particle, if it's coming in at an angle,
Yeah.
right, to the instead of perpendicularly to the magnetic field, but at an angle, I can think of this velocity vector as being composed of two components that are perpendicular to one another. The component of the velocity that's perpendicular to the magnetic field, that's going to result in the particle going around. But the other component is going to be unaffected, so therefore it'll stay the same.
Okay.
So it has to still rise but now as it goes around.
Right.
But if it's going like this, then this one has this component which is going to make it go around, and the other component is going to make it go down.
Gotcha.
So it'll do, in other words, there are two parts to the motion. There's going to be the circular motion due to one of the components of velocity vector, and the other one is just going to be along the magnetic field, unaffected, not speeding up, not slowing down, right, from the
So-
other component of the velocity vector.
If it was really close to 90, but just slightly off, it would just take
Longer.
significantly more.
Exactly.
Okay.
Time to the trip.
That makes sense.
Does that mean at the very small percent that is totally 90, there's just a bunch of particles there?
No,
It could
that's-
also be coming in, and the radius may be so big that it still hits the Earth over here, and I guess some of them do. then it depends on how far this is, you know, this radius. Depending on the speed, the radius is gonna be different. Um, by the way,
No, never mind, go ahead.
The generation of the Earth's magnetic field is actually a mystery. I mean, a lot is known about the Earth's magnetic field, but a lot is also unknown. There are many questions that are unanswered. For example, right, you know, today, tomorrow, yesterday, for the last few thousand years, or many thousands of years, you know, the magnetic field has been like this, coming out the South Pole, wrapping around, going to the North Pole. But the strength of the Earth's magnetic field is actually decreasing. It's getting weaker. It's going to zero. If it continues to decrease at the rate that it is decreasing today, they estimate that in about another 1,000 years, couple of thousand years, it's going to be zero. I'm not worried about that because I'm not going to be around in 1,000 years. But nevertheless, the people who then live, if there are still people living on Earth, right, as we kill each other, nuclear war, whatever, it's going to be a problem for them, right? Because, so for example, why is it decreasing? Nobody knows. But suppose what would happen if the Earth's magnetic field went to zero? And it stayed at zero for a long time, which there's no way to predict when it goes to zero. First of all, when is it going to be zero? Just an estimate, you know, if it continues to decrease the way it's decreasing, it'll take another 1,000 years or so. But why is it decreasing? Nobody knows. If it goes to zero, how long is it going to stay at zero? Nobody knows. Right? But suppose it stays at zero a long time, a very long time, and the sun keeps spinning towards the Earth, right? Those ejections from the sun coming towards the Earth, people tend to call them the solar wind. I mean, the solar wind kind of may give you the impression that maybe it's wind coming from behind the sun and blows around the sun, and no, there's nothing coming from behind the sun, right? It's the sun spitting. I like to think of it as spitting, right? You know, well, they call them ejections and so, but, you know, so, but this stuff coming from the sun towards the Earth, right? You know, the sun could literally blow away the atmosphere if it does it for a very long time. And then we'll have less oxygen, you know, definitely a problem for people who live here then. You know, like Mars is a planet that has you know, not a lot of atmosphere, but the magnetic field is weaker than that of the Earth. So, you know, so maybe that's what happened, right? The magnetic field went to zero, it stayed near zero for a long time, and the sun just, you know, just kind of blew away the atmosphere from Mars. Right? So, what people know about the Earth's magnetic field, or have noticed, is that the magnetic field hasn't always been this way. There were times when the magnetic field was the other way. The magnetic field was coming out of the north and then went around. Right? And it was like that for a long time, for maybe 250,000 years, something like that. And then it goes to zero, and then it flips for another 400,000 years. And then it goes to zero, and then it flips. And you know, it takes, you know, they know how long it stayed at zero. How do they know that?
Don't the poles move too?
What's that?
Aren't the poles moving? It's not exactly like at the top of the earth.
Yeah, that's another thing. And actually, that, you know, the magnetic field comes out like over here, like if this is where Santa lives, the center of this region over here is like, you know, like 800 miles or so from that. So it's a little off. That's why I kind of did it like, that was deliberate. It's not exactly at the North Pole, but, you know, it's a little off. But how do they know that the Earth's magnetic field flipped? So, do we have time? Yeah. Did I talk about magnetic domains the other day or no?
I think so.
No. Well, there are bar magnets. We have magnets in the lab, but we have bar magnets in the lab. So
Magnets.
if you think of a bar magnet, what did we say gives rise to magnetic fields?
Moving charges.
Moving charges, moving electric charges, right? And what happens if there's a wire with current in it? Well, what is a current in a wire? Just a whole bunch of free electrons moving down the wire, right? And those electrons are charged. So some people say, magnetic fields are produced by electric currents. Well, yeah, but what is an electric current? It's a whole bunch of moving charges, right? Or you can see it mathematically from here. Right? Currents produce magnetic fields. Gauss's law. Charges produce electric fields. If you write down Gauss's law for magnetism like this, like a surface integral, that turns out to be zero on the right hand side. If this were something other than zero, then we would say magnetic charges produce magnetic fields. But this is zero, so there are no magnetic charges in nature. But there are magnetic fields. Well, they're produced by moving electric charges. So why would this marker not be magnetic while a bar magnet be magnetic? What are the moving charges? Well, what's any object made of? Atoms. And what do the atoms have? They have nucleus, right? What's in the nucleus? Neutrons that don't have any charge, so I don't care about them as far as this discussion is concerned. And protons in the nucleus. So the nucleus of an atom is positively charged. And the nucleus of the atoms, right, in the material, solid, whatever, they're jiggling in a solid. Solid charges that are moving, right? But what else do atoms have? Electrons going around them. And the electrons are charged particles, right, going around. So there you have charged particles. So this marker has a whole bunch of atoms, but why does it not produce a magnetic field? Well, what happens is that the atoms are producing magnetic fields, but the interactions between the atoms is such that it's not strong, and so they produce magnetic fields in random directions which average out to zero. So if you have the marker, and move this out of your way, if you have the marker like this, there's one atom over here, and let's say that atom, because of producing magnetic field right there like that. What about this other atom here? Because of blue root, maybe produces a magnetic field like that. And this other atom over here produces a magnetic field like that. And another atom over here is the magnetic field like that, and another one like that. So this cancels that, this cancels that. Overall, the magnetic field just averages out to zero. But there are materials where the interactions between the atoms, the electrons, and whatever is responsible for the magnetism of the material, some materials have magnetic properties because of the free electrons. They're called itinerant magnets, like iron. Other materials have magnetic properties not because of the free electrons, but because of the core electrons, the ones that remain going around the nucleus. Other materials have magnetic properties because of the nuclei doing this. Right? So there are there's a host of different materials. But if it's not magnetic, what happens is that, yes, it's made up of atoms with charges that are moving around, but the average magnetic field at any point just turns out to be zero. But materials like nickel, cobalt, iron, there's a strong interaction between the atoms. And what happens is that there are regions, let's say in that region of the bar, let's say this is an iron bar. Over that region, the atoms in here interact and they produce, let's say, a magnetic field like this. let's just say that in that region, all the atoms are like, they interact with one another in such a way that it's like they line up and produce a magnetic field that way. Let me just say it like that without getting it too complicated. There's another region over here. In fact, let me change this direction. How about I make it like this? There's another region over here where the atoms line up and maybe they interact and they face this way. So they produce a magnetic field that way. Maybe this one is like that. Okay, I'll just. Each one of these regions is called a magnetic domain. I like to think of this as this iron bar is the Lewis building. And each one of these sections is like the classrooms. So this is Lewis 201. Let's say this is 201. And this is where you have a lab, I don't know, 209 or 8, whatever. So you can think of these magnetic domains as different compartments. So how are they lined up like this? Well, all of you, if each one of you were an atom, you're facing this way, you're facing this way, you're facing this way, you're facing this way. Well, you're all interacting right now in such a way that at least during the duration of the class, you're all facing this way. So you're lined up. This is a magnetic domain. And people in the other room, they're actually facing this way. But people in the classroom in the corner, they're facing that way. In the lab, where you do the 185 lab, they're facing that way. In the corner by the restrooms, in our lab, they're facing this way, right? So these are like, there are interactions, of course, because in that group they have another class, and the interaction between them causes the students to face this way, because the board is that way, and so on, right? But imagine, and these magnetic domains are microscopic in size. They're tiny. Now, what would happen if maybe some cops, OCC police, came over there with a loudspeaker and said, "Everybody in the Lewis building, face towards the Merrimack parking lot." And then you go like that, and then you face this way, right? You'll face that way. People in that classroom face that way, in the other that way. In the lab, they face that way. People downstairs in the marine stuff, they face that way. So everyone in the room faces that way. Well, that's, someone from outside would say, "Everybody, face towards the parking lot," right? Well, how do we tell the atoms to face that way? Obviously, we don't talk to the atoms and say, "Hey, face that way now." So what you do is you bring another magnet, something that produces a strong magnetic field, and you put it like this. So this is a strong external magnetic field. And what will happen, we're going to talk about this. I wrote this formula today. This is the force that a magnetic field exerts on a point charge moving with a velocity. Next, there's a formula for the force that a magnetic field will exert on a wire with current in it. And the expression is this. You'll see it. It's in the next page. And we'll talk about, okay, what are all the cases when the force on this wire is going to be 0? Well, if the wire has no length, well, that means you don't have a wire. Or if the current, what happens if the wire has no current in it? Then there's not going to be a magnetic force in it. But what happens if the wire has a current and it is in a magnetic field region? Well, as long as the wire doesn't point in the same direction as the magnetic field, or the current is in the same direction or opposite direction to the magnetic field, then the force is going to be 0 on the wire. And we're also going to talk about the torque exerted by a magnetic field on a loop. Because what happens if the wire is a coil with current in it. And we place this coil in the external magnetic field. So the different segments of the wire will experience forces in different directions, and the coil may turn. In fact, it will turn, depending on how you orient it, right? We'll discuss about the orientations that will lead to zero torque on the coil. But the possibility, depending on how the coil is oriented relative to the external magnetic field, is that it will experience a turn, a torque, which will make it turn. So what happens in this region is that, you can think of those electrons going around the nuclei of the atoms as tiny current loops. And when subjected to a strong external magnetic field, those tiny current loops in the atoms will then experience a torque and turn so that they line up, is what we say. And so what will happen is that it's like all the people in this building will then be facing towards the Gary Mack parking lot. So that's B. But now, this domain, magnetic domain, is now microscopic. Now it's the whole building. It's not just this classroom, microscopic. Now it's the whole building. It's now macroscopic. And now you don't have these divisions because you just have like one huge macroscopic compartment. So you don't have that, you don't have that, you don't have. It's just one big compartment. And what's interesting about this is that then, imagine the cop comes and says, everybody face the Lewis parking lot, right? And we all face that way. And then we stay there, and then they leave, and they don't tell us anything, and we stay facing that way. So that's what happens if you then remove this strong external magnetic field. If you remove it, they stay lined up like that. And now what you have done is you have magnetized the bar magnet. And it is as strong as it can ever get because all the atoms in the material are lined up. But wait a minute. You can then say that the magnetic field line comes out over here. Well, it must have been coming in over here, right? And did we talk about this last time or no? So then what really happens is that this magnetic field is going to wrap around, right? Right? That's what's going to happen. So now we have a magnetized bar magnet, and we talked about why this is called the north end of the magnet. The north magnetic pole, and this one is the south magnetic pole, instead of in and out. North and south magnetic pole. Yes? So, next week, you have a test on Wednesday? So how about we don't do a lab next Monday? But then, if you don't do, the people on Monday do not do a lab, then the people on Wednesday won't do a lab either. So how about the week after that, when we come back, let's do an experiment where I'm gonna give you a bar magnet, like this. And then I want you to measure the magnetic field generated by the bar magnet along this axis, like for various distances. Away along that axis. And also measure it along this axis for various positions. And then you get the magnetic field over here as a function of this distance. And I want you to do a plot. And I want you to get a functional dependence of how the strength of the magnetic field depends on distance. And the same thing over here, right? So as a function of this distance, it can be as a function of x, which you're gonna get from doing another plot. You just get the data, and then you just do a fit to see what the functional dependence is. So in 2 weeks, let's measure the magnetic field generated by one of these magnets. And the magnetic field strength along this axis is different from the magnetic field strength along that axis, so you'll see that they're different. Okay, so we'll do that.
Professor, the lab that we did Monday that they're doing today, is it gonna be due next week or the following week? The following week?
Yeah, I'm good with that.
Cool, thank you.
Yeah. All right.